Every day.
Okay, welcome everyone. Welcome. So today it's my pleasure to introduce two local speakers, Dan and Jan, and this is the day without last names, as I mentioned earlier. So our first speaker, Dan, and you can teach now everyone how to pronounce your last name correctly. So speak up, Dan. So Dan.
Milisavljevic.
See? That's the way how you do it.
Just also practice and repeat after you.
See? Now you got practice, yes. So Dan is a postdoctoral fellow in CFA. He grew up in Ontario, Canada. He then received his undergrad education at McMaster University. Then he was awarded the Commonwealth Scholarship to study at the London School of Economics in the UK, where he pursued the Master of Science thesis, Master of Science, and in 2011 he obtained his PhD from Dartmouth College. And then specializes in observational work in supernovae and supernova remnants, and he's also known for aiding in the discovery of few moons in solar systems. Okay, so Dan, please.
Thank you for that very nice introduction, obviously taken from my Wikipedia entry that some students wrote many years ago. That's very nice. It's a pleasure to be here today. Thank you for asking me to speak. I like to think of myself as a reporter of the universe, and today I got a cool story to sell you. I'm going to start with a specific case scenario. It's a personal narrative of sorts, and then I'm going to try and place it in a larger context of supernovae, their progenitor stars, and as the title alludes to, the eruptions that they have preluding those supernovae. Before I go into this, I would like to point out that I work with a lot of very bright, enthusiastic, helpful people, my supernova friends. If you're in the audience, great. They're always ready to act on any supernova alerts that may come up. You know, my supervisor, Dan Patinotti, may be doing a marathon. Raphael Margutti may be playing guitar in Italy somewhere, or you may be scaling a glacier like Klaus Franzen, but they're always ready to be there to act on these things, and I do value their input. So, the big questions that I'm trying to answer, and to place us in, we're zooming back with the director's lens to kind of get where we're placed right now, is with supernovae, trying to understand the stars that explode and their explosion mechanisms, the progenitor systems and how they explode. These are the big questions that drive my research. We know that lots of different types of stars explode by the lots of different types of spectra and emission properties that we see in the thousands of supernovae that we've discovered to date. We started with a general classification of type 1 being lack of hydrogen features, and type 2 being conspicuous hydrogen features in the optical spectra, but that has evolved considerably, and there's been so many bifurcations in that classification scheme. We also have this kind of cartoon Astro 101 understanding of how they explode, whereas a massive star goes through successive stages of nuclear fusion at its core, starting with hydrogen, then helium, building up to iron until that fusion is no longer exothermic and it's endothermic, and there's a collapse. And then something happens involving neutron degeneracy pressure, this halting of the collapse, this bounce shock that's supposed to disrupt the star. But there are a lot of details that we still have yet to understand, and it perplexes us. And this is the kind of maelstrom that I've thrown myself into. Now let's start with a little bit of a personal story. It all started at MMT about a year and a half ago, May 2014. And as part of my program to look at supernovae several months to years after they explode. I like this because it's not part of the rush that most people do, try and go after them right away. All right, I stay back, wait till the dust settles, in some cases almost literally, and look at their nebular emissions. This is a phase at which expansion has allowed the opacities to go down, and you can see emission from the metal-rich debris, the innards of the supernova. And this has very crucial information about how the explosion proceeded, the kinematic and chemical information there. One of the targets on my list was 2014C. Now in May, at these coordinates, it was just coming up from behind the sun. And previously, it had been discovered in January, where it was just hiding behind the sun. And it was classified as a type 1b. 1b. 1 being lack of hydrogen features, B meaning conspicuous helium features, which we see here and elsewhere. Well, funny thing happened with this observation. Here's the 1D, here's the raw 2D, which may be meaningful for some people. Here's dispersion, wavelengths increasing in this direction, and this is spatial. Okay? This is the trace here along the supernova. Here's the oxygen emission, which was I anticipating. Now the H-alpha emission, and you can see that it was strong, far stronger than the oxygen, and it had real dispersion to it. It was not unresolved like the H2 region line right there, H-alpha. Now this was interesting. It was a type 1b, and yet it had hydrogen. This is not supposed to be. This is how the classification scheme works, right? And this was not, again, associated with the host galaxy emission, because as I've blown it up here, you can see that the dispersion is of order 1,000 kilometers per second. And for reference here, because I know not everybody looks at this all the time, I've overplotted 2008D. This is a very well-known 1B spectrum in red. And you follow along, and there's these narrow lines. This is associated with the host environment, not the supernova. And notice how it's not as spread. Now, one may say that this is slight, but the details are important here. And this is definitely a new feature that it evolved. All the other features are basically consistent with the type 1b, except this new hydrogen extended feature. So something I'm going to say extraordinary happened while the supernova was hiding behind the sun. And the explanation that I've been working off of, and it's the best explanation to date, and the one that we're going to have difficulty reconciling with what we think we know about the evolution of massive stars today, is that the supernova encountered a massive hydrogen-rich shell, and presumably made from material stripped from the progenitor star. Okay? So this was a star largely lacking hydrogen, like a Wolf-Rayet, which are typically invoked as progenitor systems. This kind of naked supernova exploded, proceeded to interact with the mass loss material, the hydrogen that was stripped some time ago. Seems like it should make sense, but let's dig in a little bit deeper. Given what we know about the supernova, and here's the subsequent evolution, it continues to evolve to this day. And I'll show you a whole orchestra of facilities that we have that have been monitoring this. The H-alpha line continued to grow stronger relative to the others, as well as the O3. Some interesting emission lines that I'll show you afterwards as well. When you do the numbers and you look at the analysis, it seems as though that the interaction started at some radius greater than about 10 to the 16 centimeters. And likely, there was approximately 1 solar mass of material that it was interacting with. This is actually fairly small radius. Discuss that in a second. What's nice about our case is that the transition was caught early enough so that the entire slow metamorphosis could be monitored. There was a previous incident of 2001 EM, which I won't discuss right now, where it had this one ratty spectra of a type 1bc that 2+ years later showed just a narrow H-alpha feature like this, nothing else, none of this beautiful emission here. And so it interpreted the same way of interacting with a previous CSM shell. And these are neat because they fill the gap between two sets of events. One, the we call them type 2Ns. These are massive stars, generally 40 plus solar masses, hydrogen-rich, that have hydrogen-rich CSM environments, kind of like an LBV, and exploding into it, where the interaction between the supernova and the environment is immediate. Then you have the majority of type 1 BCs, right? Recall, this was an unusual event to me. I don't see this all the time, where these are infrequent, right? The majority of type 1 BCs do not show this interaction. This was somewhere caught in the middle, and thankfully it was near enough to be able to see it in detail. A lot of wonderful physics going on here that I'm going to have to brush through because I'm limited on time. This is an enlargement of this spectrum right here. And what we have here is a combination of emission from various regions. The broad, the metal-rich ejecta that's being presumably excited by the reverse shock. Because at this, and some also material that's being excited from the inside by radioactive heating of cobalt-56. You have the shocked, so this is the forward shock that's run into dense CSM, forming this H-alpha and the H-beta on the side here. And you have narrow features. You can see some coronal lines in there, all the way up to iron-14, presumably associated with photoionized pre-shock material that's ahead. A lot of things going on, and here I have just a diagram going on to explain. Okay, so here's the fun thing about being in the supernova community. Whenever one's new nearby supernova is announced, everybody rushes to the Hubble archive to see if you can see your progenitor system. You want a pre-explosion image at the location of your supernova to see what type of star system was there. And everybody did this, and this is what we came up with. Right? Bummer. That happens all the time. But, funnily enough, in my personal case, given the interest in the object, we were able to apply and successfully be awarded time with Hubble. And during preparation of the Hubble observations using this APT software, a funny thing happened. Okay? So in red is the footprint, and here is the proposal ID and the detector. And there is the location of 2014C. So as I went through, and because I wanted to position the detector just so that if there were previous images, I could make a nice mosaic and make a nice color image, etc. Okay, so if you go through, you can see it just off the edge there, just dancing off the edge, and then off to the side, and then again with more. This is with STIS, just off to the edge, and again just off the edge. This is outer survey, and then this is the one that I showed you, right? And then again, subsequently later years, and then, bingo, all right? So amongst the dozens and dozens of images that were taken of the field, there were 3 exposures taken in the H-alpha filter, funnily enough, of the region. Here you can see a larger scale and enlargement. And thankfully enough, we just happened to be able to find Subaru images of the region as well, with a source coincident with the supernova, which was pretty neat. And what's nice about this, though it doesn't come through very nice on the screen here, is that this is one of the best detections of a progenitor system of a type 1 BC. State of the art so far has been like a pixel or 2 or 3. All right, I have tens of pixels, man. This is kicking. All right, now unfortunately it was only one filter, right? But H-alpha filter ends up being an interesting one in helping set the SED of the region. Okay, so we resolve it. It's resolved by Hubble, and it's about 1/4 of an arcsecond in size, which works out to be about 15 parsecs. You know, this, along with other things, led me to conclude that it was most likely not just a single star, but some kind of compact cluster that it was associated with. Also consistent with this is the fact that if you look at the centroid, that's where the X is, you can see that it's slightly offset. Right? Now the wonderful thing is, now that this is, we have these pre-explosion images, we took an image with with Hubble. So now we'll be able to pinpoint for sure where the supernova is, and then years later see what emission fades to be able to tell how strong of an H-alpha source that was at that location. Okay, so if you look at the SED, there's the BVR images, there's the H-alpha emission. You model it with B-pass stellar models thanks to J.J. Eldridge, and we find an age, interestingly, older age, of 30 to 300 million years. And this corresponds to a mass range of 3.5 to 9.5 solar masses. And the models favor interacting binaries. Now, how do you do that? This is in the physics that JJ will explain more closely, but in the interaction scenarios, the H-alpha emission is stronger between them, the shocks and the winds. So in his models, he found that interacting binaries worked better. Okay, so the most important questions, and now we're going to start looking at the larger issues at stake here. Okay, I found what's kind of a neat object, but what's the significance of this single object amongst all that we know? I said it was rare, but how rare is it? And the other thing is, what is the origin of this CSM shell? Okay, now I mentioned earlier that there's some problems with the shell, and this is where it starts to creep into place. Here's Stellar Evolution 101, and this is how I learned it in grad school, that for various mass ranges, the star will go through these various sequences, originally called the Conti scenario sorts. Through massive star winds, it'll go through some kind of LBV or Wolf-Rayet stage, right, until it reaches a terminal supernova explosion. Now, when you look at these progressions, however, and you realize these assumptions, that the LBV is a transitional, i.e. not end state, and lasts 10,000 to 100,000 years, and the Wolf-Rayet stage lasts several hundreds thousands of years. It's unusual then that we're finding stars that may be in the LBV state at the time of explosion. And this is shown in many situations, which I'm going to review right now. Red is a bad color there. But we recognize major problems with this classic scenario. And here's one that we've talked a lot about here at the CFA. Supernova 2009 IP is a silly name because the supernova actually happened in 2012. But in 2009, there was a supernova imposter. There was an LBV-like outburst that fooled us into thinking that supernova was taking place. But monitoring the light curve over years, you could see that there was these kind of precursor activity going on before the supernova explosion. And this is not a freak incident. The regularity of these things is becoming difficult to understand. In this case, we have another supernova, 2010 MC, where I've done no scaling other than just correcting for the distance in an absolute magnitude. And you can see this kind of coincident light curve. Some believe that this is the actual supernova explosion here, and this is the subsequent interaction with the CSM. Okay. So stars are doing things right before explosion, when classically I was taught that information in the core is not transmitted to the envelope. Right? The density gradients are so large, and an instability of that scale should disrupt the star completely and not be able to work on time scales of years. Many other examples here. An important Optical paper showed that in type 2n supernovae, perhaps as much as 50% of these supernovae experienced precursor activity within a few months of core collapse. That was from a sample of 16. And Corsi et al. Found suggestive evidence of a precursor activity a couple of years before the supernova. Here's the light curve. Here's zero flux. Here's the binned data points where you could see it's slightly above. We're chasing ghosts at this point, but they're very suggestive. It's difficult because, this is 5 magnitudes, 100 times less luminous. Very difficult to find this precursor activity, especially at great distances. Here is kind of one of the first examples of this eruptive precursor activity. I was, again, this is one of my first observing trips, and there is a report of a supernova, 2006 JC, right here. And the Japanese amateur astronomer, who I hardly call amateur, by day he runs a snack company where they package peanuts. And by night he has an observatory of many telescopes that he goes and uses to search for supernovae. And 2 years previous he had detected a blip there that lasted no more than a month. And this was me at the telescope actually blinking the images to make sure that it was legitimate. This was an unusual explosion, different from what I showed you in 2014C, in that it had helium-rich emission lines. I showed you hydrogen-rich emission, helium-weak. This had very little hydrogen in emission and lots of helium. Okay. I'm going to just scoot ahead here. And yet another example, these are radial light curves. So this is days since supernova, which translate, it's probing years before the supernova. And essentially, in the case of a smooth wind, these lines should be going across like this, but you can see real modulations in the light curves associated with density jumps in the CSM. Again, not consistent with smooth winds. Okay, so we're trying to understand what's going on, right? Scenario 1 of 2014C and objects that may be like it. Could it have been a Wolf-Rayet bubble? That's what I originally thought. Hey, it's a hydrogen-poor star interacting with a CSM, and I see these glorious kinds of pictures all the time, right? Problem is, Wolf-Rayet bubbles are normally around a parsec, larger in size, and this was much smaller, right? 100 times smaller. And it's hard in simulations that go through the formation of Wolf-Rayet bubble to be able to contain a bubble of this size around the star, especially if the star goes through a process of 100,000 years of winds that are about 1,000 kilometers per second. The momentum is just too strong. This is possible if the Wolf-Rayet phase was unusually short and or if the mass loss was extremely asymmetric. The real key thing here is a short Wolf-Rayet phase. Okay. Another thing, could it have been an LBV-like outburst? There's many things about the environment that say this is unlikely, right? Especially because the modeling that we do favor stars that are much less massive than the 20 solar masses and above that we think to be a minimum to be associated with LBV outbursts, right? And also these LBVs and the type 2N supernova they've been associated with are generally hydrogen-rich, right? This was hydrogen-poor, and we don't see Wolf-Rayet stars going through this kind of eruptive phases. Another scenario that I find very interesting is that perhaps neighboring stars are contributing radiative flux that's kind of helping to confine the wind, or perhaps there's the thermal pressure of neighboring stars helping to confine. This is work by Jonathan Mackey, who finds that radiation from neighboring stars can form a photoionization confined shell that traps up to 35% of all mass lost during the red supergiant phase. By the way, there's Betelgeuse, to which the model was applied to. But again, this was a hydrogen-poor star, right? So it presumably was a Wolf-Rayet star, and a Wolf-Rayet phase lasting 100,000 years with these kinds of winds would have destroyed such a bubble. Now you can start try to save the phenomenon by saying that maybe the original shell was very massive, so it destroyed a good portion of that, but some of it still remained. But that's only possible if the Wolf-Rayet phase was fairly short, generally. And oh yeah, by the way, this is the neat Herschel image of Betelgeuse that this was applied for. So here is the photoionization confined shell that they go on. There's the bow shock. And there's another interaction right there. And here's the punchline. Okay? Out of everything that I talked about the specific case of having stumbled onto a hydrogen-poor supernova explosion that seems to be interacting with mass loss confined to some shell at some distance away. How did it get there? Right? Why was it there at the time of explosion? And the time scales are such that it seems to have been formed fairly close to the time of core collapse. There is a sort of synchronization between that ejected envelope, perhaps common envelope, right? An ejection and the core collapse. Tying it all together, this kind of precursor activity, the fact that stars are doing things in the years to decades to centuries before explosion, makes one to think that indeed there's activity from the core that's being transmitted to the envelope. The instabilities are somehow making their way out. Here's a simulation by Arnett and Meakin trying to show a realistic interior star towards core collapse. This is not the onion skin model that we all know, right? This is quite turbulent. Right? And in fact, these turbulences may be associated with a lot of the mixing that the supernova explosion experiences as it goes. Here I did work with a three-dimensional reconstruction of the supernova remnant Cassiopeia A, not just looking at the shock material, but the interior unshocked, and it shows this bubble-like structure. Right? And it shows the iron having been mixed much further out, as traced in the X-ray. The iron mixed much further out than a normal core collapse explosion should. So it may be that these instabilities are perturbing the star structure that's enabling the explosion to take place and encouraging the development of mixing in the star. That's how I'm trying to put everything together. There's a lot more to come. I thank the TAC for being helpful with getting access to MMT to do this kind of research, because between all these things, we've been able to have all these facilities track the supernova because of the interaction. And this is all work coming up in the not-too-distant future as we continue to monitor this and other systems like it. So look out for these and other interesting physics. I talked about this already, and I think I'm about time. Thank you very much.
Thank you, Dan. Questions? Yes, back.
You know, if there had been a binary interaction, you might expect the companion to still be there someplace, although perhaps in a somewhat, excited state. Are your observations able to, with HST, for example, able to tell anything like that?
From the observations that we have, we'll be able to do a subtraction between what was there and what's there after the explosion, right? So we'll subtract the star that was there. I'd be curious to know, what do you mean by the other companion star being excited, right?
Well, it's just been in the middle of a supernova.
Right. I don't want to be, my guess is that it would be very difficult to be able to pin out that star from the cluster, given that it is. But we know very little about that cluster. It's possible that going with longer observations and with the full suite of HST observations and other filters may be able to pin out more. For instance, wouldn't it be interesting using a helium-1 filter to look at, for instance, other Wolf-Rayet stars in that vicinity or something? Yeah.
That's fantastic work. Really
Oh, okay. Thank you.
Are there Chandra observations, and if so, can you tell us anything about the interaction of the expanding material with the certain cell material?
There are incredible Chandra observations. Incredible, that have been coordinated with NuStar. And that's work that Raffaele Margutti is coming up with very shortly. And she places she goes into detail about constraining the physical properties of that CSM shell. So she comes up with a mass, something about its composition, and right. I think I'm going to leave it at that. So you can look for her, but definitely there are observations, and it's been following through multiple epochs, watching actually as the X-ray light curve rose over the course of a year and a half, and continuing to monitoring over the next couple of years, I understand.
Okay. Alex, you have last question.
So, question on timescales. So you observe this interaction between the shell and the supernova reports, and the supernova explodes roughly a year later, or half a year later.
4 months, etc. Yeah.
And then you showed, the pre-supernova activity, which happens on the timescales of maybe a couple of years before the explosion. So, did I get it right that you related, the shell with something, this flaring that happens a couple of years before the explosion? And if so, how would you reconcile velocities that would be required to place that material?
Exactly. So you're right. I'm grabbing from scraps of material in the sense of, hey, look, this star seems to be doing things beforehand. In the one case I showed you was 2009 IP, and those were timescales about a year to months beforehand, right? But in that case, the interaction was immediate, right? So the shell was nearby. In this case, the interaction was months later, so the timescale becomes decades, essentially, or 100 years, right? The ejection of the shell should be of order 100 kilometers per second, and you do the math, et cetera. That's where I come up with this rough estimate of 3 times 10 to the 16. There are radio observations that should be able to put a firm number on the forward shock velocity. But that's exactly right. The time scales between the two are different.
Okay, thank you very much.
Thank you. And he gets this now, right?
Yes, he gets to know. Okay, so our next speaker is Jan, who also has a difficult last name. So Jan Vrtilek is an astrophysicist at CFA. He received his PhD from Harvard University. He was a postdoc and on a staff at Columbia, Goddard, and then at CFA in the molecular astrophysics and infrared astronomy. Jan joined the Chandra project at CFA a few years before the launch of Chandra, and now Jan's major research focus is galaxy groups and clusters. However, today Jan is not going to talk about groups or clusters, but he's going to tell us about the Chandra mission planning process.
Okay.
Please.
Thank you very much, Akos, and thank you to the organizers for inviting me to give this talk, which, as Akos just said, is a little bit unusual for this series. But most of us in this room are Chandra observers. And so we have an intrinsic interest in the mission planning process from the observer's perspective, which is really, why aren't my observations all done immediately without being split up and with every one of my preferences? So what I'm going to try to do, if you forgive me, slightly cliched Wizard of Oz image, is give you a view behind the curtain of the planning process and show you where all the difficulties and limitations are that we have to contend with, how these are developing over time, and what the future prospects are for being able to execute observations the way that you want to. So, and I apologize here for the excessive simplicity, but a very crude schematic of what the CXC does for an observer, from the proposal handling process all the way through delivery, goes through planning, execution, and processing of observations. This talk is going to concentrate only on this block, on planning, and partially on the execution part. And I hear from the organizers of the talk series that in the future we may have another talk by a different CXC member on the downlink side of the operation. But that won't be for today. So let's go right into the substance. and dig into why we can't do everything that we want to all the time with Chandra. And that's basically because there are constraints on our operations, not surprisingly, as there are on all space observatories. And we'll consider two categories of constraints here that limit the timing, pointing, and characteristics of the observations. The first one is constraints to the science aspects of the operations, and that's basically set by users per their science requirements. There are all kinds of constraints, and those of you who've set them for your observations will be very familiar with them. There are window constraints, monitor constraints, you can group observations, you can request uninterrupted observations, there can be phase, role, and coordination requirements. And in addition to that, of course, the observatory is limited by spacecraft constraints, and these are set by physics and by the design of the spacecraft. So there are sun, Earth, and moon avoidances, and there are radiation zones that depend on the geometry of the orbit. And these constraints are all equivalent to time constraints in one way or another. They can all be translated to time constraints. There are, from the instrument characteristics, there are bright object avoidance restrictions. That's very rarely an issue. And then finally, there are thermal constraints. And as the observatory has aged, the surfaces are exposed to space. It's not a friendly environment, and the thermal properties change. And these are very much more complicated constraints in that they generally depend on solar pitch angle, which determines what parts of the spacecraft get hot and what parts get cold. But it's more complicated than that because there are time constants involved. And so they are dependent on a combination of solar pitch angle and pointing history. And we'll show you a little bit more of the details of what's involved in that later on. And now, once we've managed to build a schedule involving all of these complexities, we're not really done because there are interruptions to the schedule. And these, again, are of two major kinds. There are space radiation events. The frequency of occurrence of these depends on where you are on the solar cycle and on the particular characteristics of the solar cycle. Now, we have a little bit over 20 megaseconds of useful observing time in an annual Chandra observing cycle. And cycle 6 was the very worst from the standpoint of space radiation events and caused about 1.4 megaseconds loss of observing time. It's a very serious loss. The current solar cycle is comparatively much weaker, and we have substantially smaller losses at this point. Radiation events force the science instruments into a safe posture, but we no longer actually stop the satellite pointing profile, precisely because of the thermal issues that we have with a slightly older machine in space. We continue the pointing profile now, and so the satellite goes through all the pointing motions that it would if the science program were continuing. But at the same time, we've actually safed the science instruments. And this makes it much easier for us to pick up with the observations again because we have a well-determined thermal state for the satellite. Now, the second general category of interruptions that we have to contend with are targets of opportunity. We know that the X-ray sky is highly variable. And this offers high potential science reward in terms of relatively rapid responses to the changing X-ray sky. The flip side of it is that there's a high cost in terms of replanning effort. Chandra is not a real-time observatory. We run on command loads that are planned at this point on a 2-week basis and run in segments of a few days apiece. And we have only 3 ground contacts in a typical day. So a replanning effort in the middle of a load is quite costly. And the targets of opportunity may enter as peer-reviewed and then triggered observations. We have about a megasecond of those per year, or as requests for director's discretionary time, and we have about 0.7 megaseconds of that per year. Let's have a slightly closer look at the constraints that observers can impose. The table that I'm showing you is out of the call for proposals in cycle 17. It refers to peer review approved constraints. And constraints are listed down the side. We've developed a grading scheme for these constraints because implementing them is relatively expensive in terms of the difficulties it imposes on the entire planning process. We've classified them into easy, average, and difficult constraints. And we have a quota of each of these for the peer review to assign per cycle. Now, the levels that are set right here are an interesting combination of art and science because there is no easy quantitative way to set these numbers, since the only way to make sure that we don't have a level of constraints that actually break the planning process is to go through the planning process. And that's so laborious that we can do it only once. We can't run a lot of full-up simulations. So there is a combination of experience and insight and some calculation that goes into determining these numbers each year. And so far, we've been able to complete the planning processes successfully. So we're probably setting them at approximately the right level. Now, moving on to from observer constraints to constraints that are set by physics and engineering, we have a number of avoidances that are imposed on the observatory by its design. I'm going to go through these just very, very quickly. There's more detail here than we need. There's, of course, the sun avoidance that all of us are familiar with. We can get to about 46 degrees from the limb of the sun, and it makes about 15% of the sky inaccessible at any given date. There is a small moon avoidance and a bright Earth avoidance. You're going to see the consequences of some of these in graphs that I'll show you later on. The moon avoidance, for example, can be circumvented if you're willing to accept a reduced accuracy aspect solution by running just on gyros, not on the aspect camera. Here is a very simple diagram showing you the effects of sunblock. The natural coordinate system in which to think about this is ecliptic coordinates. If you're observing at ecliptic coordinates higher than plus 46 or lower than minus 46 degrees, you have no sunblock to worry about at all. If you're at ecliptic latitude 0 degrees, it takes 3 months for the source to move through this exclusion zone, and that's the worst possible condition. The Chandra orbit is a relatively interesting one. It's a very high orbit that goes very roughly out to about half the distance to the moon and comes to within a few thousand kilometers of the Earth. And that's a very advantageous orbit for many purposes. One of them being that it allows, in principle, very long uninterrupted observations of time variable objects. We're a little bit limited in that now because of the thermal considerations that I'll talk more about later. But in the beginning of the mission, that was certainly easy to do. The orbit is subject to very large perturbations since it goes this far out from the Earth, principally due to the gravity of the moon. And it goes through extreme evolutions over time. So you observe, for example, that the orbit inclination here over a period of about 20 years varies from 30 degrees all the way up to about 75 degrees. The right ascension of the ascending node shifts very substantially. You'll see this in the motion of the Earth-blocked zone in a figure that I'll show you later on. The orbital eccentricity varies from about 0.9 to about 0.6. It's a very large variation. In conjunction with the eccentricity variation, there are corresponding orbit perigee altitude variations. So the perigee varies from about 29,000 kilometers above the Earth's surface to about 3,400 kilometers. And this has particularly large effects in the way that Chandra cuts through the radiation zones. And over periods of years, the interaction with the radiation zones varies quite substantially. The length of the radiation zones, of the science shutdown during the radiation zones varies, and consequently our observing efficiency varies. It's still very high. Our mission average for observing of wall clock efficiency must run about 70% or so. This shows you sky visibility averaged over an entire year. And mostly it's very high. The contours go from 70 to 90%. And so you have approximately 70% visibility in the darkest areas and essentially 100% in the lightest areas. The major feature right here is set by the solar exclusion zone moving through the sky. And, but there's a blob right down here. And that's owing to the very highly elliptical orbit of Chandra. And you noted that the Chandra orbit is tilted so that the apogee is at this point very high up in the northern hemisphere. And of course, Chandra moves by far the slowest near its apogee. That means it spends most of its time there. And at that point, the Earth occupies the opposing point in space, which is therefore in the southern hemisphere. The Earth appears to hang in the same position very steadily for a long period of time. So in each orbit. So there is this is the so-called Earth-blocked zone, which is not, of course, fully blocked. We can observe it, but just not at some points of the orbit. And because of the inclination evolution, this blob moves by about 3 degrees per year in a vertical direction and about 10 degrees per year in a horizontal direction because of the evolution of the right ascension of the ascending node. So that much for the Chandra orbit. Once we've taken all of these issues into account, we're ready to begin on an annual development of the long-term schedule. Now, our proposals are accepted once a year, and in principle, they really should be in their final form once they go in. But in practice, of course, they're not. And there's an initial negotiation process with the observers in which we make sure that all the parameters of the observations that directly influence the planning are fixed in their final form. And then we're ready to begin the long-term scheduling process, in which we try to achieve a initially rough assessment of the thermal balance in each period in which we schedule. We used to do this in 1-week periods. We now do it in 2-week periods. That gives the flight planners who do the detailed scheduling more flexibility in the arrangement of targets. Of course, it means it's likelier that an individual planning period is going to get interrupted by a radiation event or a target of opportunity. But we've decided to take that loss, and that the overall advantages outweigh the disadvantages. We fill our the 2-week bins in which we operate at this point not quite to full capacity. We keep a pool of unconstrained targets with which we can fill out the bins. We attempt to keep large programs intact. We attempt a good thermal pitch balance as well as we can. Now, I've explained to you already that until detailed scheduling is done, we cannot determine the thermal state of the satellite because it depends on the history of the observations. So until the short-term scheduling is done, we don't actually know that we have a really good long-term schedule. But we can do a rough thermal balancing with rules of thumb that we've developed from experience. And once we're done with the long-term development process, which takes quite a few weeks each time we get new observations, and which is very laborious, the long-term schedule is published and is world-readable. We try to maintain the long-term schedule stable as well as we can so that observers have a reasonable amount of predictability about their observations. But of course, we cannot guarantee it for all the reasons that I've just outlined. And then we move into the short-term schedule process, which is a closely cooperative process with the flight engineers, in which engineering activities are interleaved with science activities. And the thermal models that we have that describe very accurately what the thermal behavior of the satellite is can be tracked from observation to observation to make sure that no thermal requirements are violated. And that generates the short-term schedules, which we then also publish, and which go on to run the satellite. A principal tool of long-term schedule development is a variant of the Spike scheduler, which is the same basic program that Space Telescope uses. This is a variation developed particularly for Chandra. And there are a few things to note about this panel. Spike, of course, cannot be aware of detailed short-term scheduling. So it's principally aware of where the sun exclusion zones are. It's aware of where user constraints are. It's aware of what resources are available in each particular 2-week period. It tells us when resources are exceeded, when bins are underfilled. And the work of building this long-term schedule is principally done by hand, beginning with the most seriously constrained observation in the longest programs and working down to the least constrained observations in a systematic fashion. Now, I told you I was going to tell you a little bit more about the time evolution of the observatory's physical properties. Most of the observatory is coated in aluminized mylar multi-layer insulation. And this insulation ages and becomes less effective over time. And the principal effect of that is that areas of the observatory that are turned toward the sun heat up more than they did at the beginning of the mission. And here you see a graph that shows this evolution from the time of launch to 2015 to the current year for a number of spots on the spacecraft. You don't particularly have to worry about what they are. But you notice that at the beginning of the mission, there was only very, very slight heating on the average. And in the last 10 years or so, there's been a steeper linear degrading of the properties. There is no reason to think that this will proceed in anything other than a predictable fashion. And this lets us look ahead quite a substantial amount of time and plan for and update thermal models and plan ahead for where the difficulties are going to be with developing emission schedules. And here you see a similar graph developed for the average temperature of the optical bench. Again, for the first few years of the mission, it's quite stable, and then there's a generally linear increase and greater variability across short periods of time. And as we develop experience with the systems, we can cautiously raise the yellow warning and the red warning levels for the various parts of the hardware that will allow this. Not all parts do. There are quite a few thermal restrictions that are imposed on us right now, and they apply at almost all solar pitch angles. So here we have the power supply and motor controller for the science instrument module, the momentum unloading propulsion system, the integral propulsion system fuel tank, and so on and on. And you see that there's really no accessible pitch angle to the satellite that's unaffected by some thermal restriction. And here is a list of the active constraints under which we're operating, watch list items where we think there may be future constraints, and notes where future problems may arise. I think this is intended to emphasize to you what the complexity of this problem really is. And not surprisingly, what it results in is the development of individual schedules that are basically a dance between all of these restrictions. And it explains to you why you've been seeing in the observations that you get back more and more splitting into shorter blocks. Because if we run into a thermal restriction, we may have to stop an observation, go to another observation that's affected by different restrictions, but relieves the first one, and then go back to the observation again. So what you're seeing is a larger and larger number of shorter and shorter observation segments that are forced by the thermal evolution of the satellite. And there's nothing we can do about it, but we can manage it. And we can still meet most of the scientific requirements of the observers. And here is a different view of the same problem. And it shows you a kind of summary of major restrictions and what pitch angles they affect and what lengths of observations they will allow. And it also tells you that the very small eccentricity of the Earth actually affects the thermal state of the satellite, and that the restrictions are somewhat different at perihelion and at aphelion. The next figure illustrates the dance that I was just talking about and shows you, one of our critical temperatures and its evolution during a 2-week load. The red zones are the rad zones, and here you see the temperature that's being tracked as a function of time. And the planning limit is the line across the top, and you can see that we're continuously varying, getting close to it, and then scheduling something that moves us away again. But of course, you have to imagine that there's an entire stack of these diagrams affecting different temperatures throughout the satellite. And we have to keep below the horizontal line on every one of the diagrams at the same time. So it's a somewhat complicated problem. And essential in doing this problem correctly is a very well-developed set of thermal models for the satellite that, given the initial conditions at the beginning of a low development, we can reliably propagate forward knowledge of the temperatures depending on the observations that we schedule. A recently evolving temperature issue, I see I have just a couple of minutes, so I'm going to go through this fairly quickly, has to do with the aspect camera. The Chandra, the stability of acquisition and pointing, as well as the accurate reconstruction of Chandra aspect, is done by the aspect camera, which in its most stripped down form can be described as a 4-inch camera lens with a very long focal length, illuminating a CCD with about a 1.4 degree field of view. And it is sensitive to stars down to nearly 11th magnitude. And it is also temperature sensitive because the effective background increases as temperature increases at the ACA CCD. and increased temperatures result in larger numbers of hot and warm pixels. And here you can see an illustration for temperatures of -15, -10, and -5 degrees at the aspect camera CCD. And you can see the increasing difficulty of detecting the star that we're trying to lock onto. This is a 10.6 magnitude star that's being illustrated here, and you'll see that the scale here, when I talk about increasing background, the images look fairly similar, but you'll see that the scale varies from about a factor of 3 from this image to this image. So the next picture shows you, again, a pitch diagram and shows you where the very large pitch range over which these thermal issues arise with the ACA, and the relatively lesser pitch range over which we're in positions where the ACA can be pointed to cool it down. So again, there's this dance in which we move back and forth across solar pitch ranges in order to keep a critical piece of apparatus colder. And as time goes on, this is going to lead to planning difficulties because we will find that we may have too warm aspect camera CCD and reduce sensitivity to stars in fields where we cannot find enough stars for acquisition and pointing and guidance. So we've now developed a collection of software tools which let us look ahead through the length of the entire mission. When we obtain a new batch of proposals at the beginning of a cycle, we can examine every observation in advance throughout the entire year. We step in fine time intervals throughout the year. And at each time interval, we look through a range of possible roll angles, from the nominal roll angle to through the full allowed range of off-nominal roll angles, and check to see what CCD temperature would have to be attained in order to give us a sufficiency of stars for operating. And then we can make time plots of these things, both at the nominal roll angle and checking all possible roll angles to see what the time intervals are at which the observation can be taken. And you can see that this gives us a whole new fence of time constraints within which we're going to have to do our planning. I'm running a little bit out of time, so I'm going to skip over some of the details of replanning that I was going to go through. This is a fun diagram for those of you who haven't seen it, in a certain sense of fun. This shows you the Advanced Composition Explorer ACE particle detection rates. We use that to inform ourselves about the radiation environment in which Chandra operates. Each line here represents an order of magnitude on a logarithmic scale. And you can see that when the space weather gets unpleasant, particle radiation densities can change by several orders of magnitude. And if any parameter of Earth weather changed by several orders of magnitude, we would be very, very unhappy. Space weather can be a rough environment. So that was just meant to illustrate this. And I'm coming right to the end of my time. So what I want to tell you about now is what we really all care about most as observers. What is the future outlook? So let's go over, the key points. I've spent half an hour telling you why this is all difficult. And now I'm going to tell you why it's all actually quite good. At the end of 16 years of operations, we have a very complicated 5-ton spacecraft, almost all of which is operating in an entirely nominal fashion. This is terrific news. We have actually no major limitations on the spacecraft. The thermal evolution, for all of its complexity, is slowly changing and is well modeled and well understood. And we can look ahead so that we're ready to adapt our planning as it develops. For expendables, we have only the momentum unloading propulsion system propellant. I didn't tell you very much about that because it's really not an issue. We're using it substantially less rapidly than initial planning, initial design of the mission allowed for. We have decades of reserves, and there's a possibility of even operating entirely without it, if there should be a need to do that. The detectors are stable. Our major detector issue is the slow accumulation of a very thin contaminant layer that affects some reduction of the effective area at low energies. It's not a major problem for most of our science. And our external support is very strong. A good measure of the support from the scientific community is our proposal pressure. And that is steady and high throughout the entire mission and shows no sign of any substantial decline. And our general outlook for support from NASA is very positive. So we have solid hardware. We're running the mission in a very conservative fashion, and we're very proactive about looking ahead for possible difficulties. And Chandra continues to give us irreplaceable science contributions. So it looks as we have every rational reason to look forward to extended operations for a long time yet. Thank you.
Thank you, Jan. Questions? Yes.
Do the type of CCDs show any sensitivity to radiation damage? And their coronal mass ejections occurring occasionally in other hostile environments?
Yeah. Well, they certainly did at the very beginning of the mission. There were very rapid changes in the CTI, and until we understood the character of the radiation damage and went through the protective measures that are now in place. But at this point, the detectors are degrading very well. I wouldn't even say degrading; they're aging very slowly. I mean, I would, for more details on that, I think, Larry is here, who heads the calibration team. I mean, you may want to make more comments on this, Larry.
The radiation damage does increase the CTI, but it's pretty slow and steady since early in the mission, so we can model it.
Yeah. So.
Do you see an incremental change after a coronal mass ejection?
I don't think so, no.
Okay, good.
Yes.
As you demonstrated, the scheduling is a notoriously detailed process. Over the lifetime of Chandra, are there areas that you've been able to automate more, and is there any prospects for that sort of thing in the future?
Yeah, certainly, yes. At the beginning of the mission, it's almost frightening to me to think back to the early days when I do it and see with how little automation we ran. There were a lot of processes that were tremendously laboriously executed by hand. Load reviews were agonizing because very, very many checks were done by hand. And of course, we automated these things as rapidly as we possibly could. And our software is getting continuously better and continuously more helpful as the problem becomes worse. So it's a race between an ever more complex problem and ever better software.
Last question.
You may have covered it before I came in, but if you're making so many changes in your loads, how is that affecting the efficiency of the time that you get out of Chandra?
Actually, very little, because we're observing every instant that we can be observing. So if we're not shut down because of a radiation event, and if we're not in a radiation zone, and we're not slewing from one target to another, we're observing. There is yes, but the slewing is a very small fraction of the time. So that yes, if we do have to repoint among more short observations, there is a slight penalty in terms of slewing time, but that's not a large factor.
Okay, I think we reached our time limit, so let's thanks Jan once again.
Oops. Okay. Oh, the microphone. Yep. I almost went back to my. Yeah, people are sometimes not aware of all the. If you don't, you don't need to be. So I hope people thought
It was interesting. Thank you very much.
Yes, it is. Justly so.